Welcome back. I had to run out and get a haircut and change my shirt, but we're ready to go. So we were just talking about k-means clustering, and you remember one of the things with k-means clustering, one of the challenges is you have to choose a number of clusters k, right? Which can be a problem, and a little later we'll talk about strategies for choosing k. But in this segment now we'll talk about hierarchical clustering, a different kind of clustering, the second major one that we'll talk about. And it has the advantage, it doesn't require the choice of k. As a matter of fact, as we'll see, it gives us the clusterings for all k all at once. And we'll talk about what's called a galometer or bottom-up hierarchical clustering, which is the most common kind of hierarchical clustering. There's also top-down hierarchical clustering you might see, but we won't talk about that in the lecture because the bottom-up or galometer is by far the most common. And we'll see that the galometer, the clustering starts from the bottom, the individual observations as leaves, and combines them successively in a hierarchy. So let's see the main idea just in a picture. So here's some data with 5 objects and 2 features in the horizontal and vertical axis. And what hierarchical clustering does is it successively joins the closest pair of objects. So first of all, I'll run through it quickly, and then we'll go back and look at the operations more slowly. So here's the data. Now let's see what hierarchical clustering does. So there's one linkage, another clustering, another one, and another one. So it did a total of 1, 2, 3, 4 joins. Let's go back more slowly now and see what happened. So starting with the raw data, it looks for the closest pair of objects in terms of squared distance. And we'll talk a little bit later. We can actually vary that, use a different metric, but usually it's squared distance. So the closest points in the plane here, the closest pair are A and C. It joins those together. Then it looks for the next closest pair, and that is D and E. Right? And then it's going to join the next closest pair. But now the idea of a pair, we're going to join not necessarily always just single observations. We might join an observation with an existing cluster, or maybe join 2 clusters. And we'll have to decide on what we mean by how far apart are 2 clusters, which we'll talk about a little later in the segment. But let's see how we've made some choice of that metric, and let's see what happens. It joined B with A and C, okay, and then finally all 5 points together in one cluster.
So in this last one, it joined 2 clusters together.
Exactly.
The big red cluster and the green cluster.
Right. So this next slide summarizes now the clustering. Again, you see here on the left the series of joins that we just saw, and now on the right is a dendrogram or clustering tree, which is a very nice way of summarizing the clustering. The picture on the left is fine when you have 2 features, but imagine if you had 100 features, we'd have to be drawing a 100-dimensional object, right? Which you can't do. The clustering tree on the right is the most useful way of summarizing the clustering. So let's see how it summarizes things. Well, here's the AC. First of all, at the bottom we have the leaves of the tree, the objects, labeled A through E. The first join is indicated here. This is the join of A and C. And the height of the join is also, this height of this join is drawn at the height at which is at the distance between the 2 points involved, right? So A and C, their square distance is here, and that's the height at which this is drawn. The next join is D and E, then B with A and C, and finally all the objects together at the top. So the clustering tree gives us a nice summary of the series of joins that we get in the clustering.
But what's it mean, a distance between a point and a cluster, Rob?
Well, we'll get to that. Do you want me to tell you right now?
No.
Okay. So here's another example. There's 45 observations, again in 2 dimensions. And in reality here, we've imagined there's 3 classes. So I've colored them as such, green, purple, and gold. But we're not going to use these class labels in the clustering. We want to see, after we do the clustering, where these points end up. So here is the result of hierarchical clustering to the 45 points. And these are all the same dendrogram. But what I've done here is I've cut off the clustering tree at different heights. On the left, I've basically cut it off at the top, so the entire tree is one cluster. Okay? That's why I've labeled all the leaves by the same color, green. But here, I've cut the clustering tree off at this height, about 9. It creates 2 clusters, which I've indicated by red and green. And then finally here, I've chosen a different cutting height, around 5. It forms three clusters: the purple, the gold, and the green. And you see the original three classes, which I colored, are actually coincide with these three clusters. So the point is that by doing the hierarchical clustering and cutting the tree off at an appropriate height, we recover exactly the three classes we started with. You can also see that now what this is showing us is that with a single operation giving us this clustering tree, we get a clustering for all k, right? If we decide we take the same tree, if we cut it off at the top, we get k equals 1. We cut it off at 9, we get k equals 2. We cut it off here, we get k equals 3. I could cut lower and get more clusters. I could cut it right at the bottom and get a cluster which had a cluster for each observation, which probably wouldn't be very useful. But the point is that we get a spectrum from 1 up to n clusters, depending on where we cut, from a single clustering tree. Okay, so this is just the details of the figure, which I have already been through. Okay, so now we talked before about how we had to decide how far apart two clusters were, or a point from a cluster. The linkage is what that's called. And now let's talk about the details of the choice of linkage. So on this slide, I've got the different linkages: complete, single, average, and centroid, and their definitions. But I think it'd be easier to go to a blank slide, and I'll have my Khan Academy moment and show you just in pictures what these measures are. So complete linkage, let's first of all think we have measure of two clusters. Okay, and this guy's already a cluster, and over here we have another cluster. And now we want to decide how far apart is this cluster of 3 from this cluster of 2. Complete linkage, first of all, the first kind, we look at the farthest distance between any pair, where we pick one object from here and one from here. So the farthest distance will be this one. Right? This pair is the farthest apart, so we deem these two clusters to be this distance apart. That's complete linkage. So it's kind of a worst case measure. Single linkage is the other one. It's the best case. We find the closest pair. And for that, it looks like it would be this pair, right? This pair would be the closest. That's single linkage. And then the average linkage is, as you can imagine, we look at all pairs and take the average distance. So we look at the distance between this guy and these two. And so how many altogether, Trevor? There's 6, I guess? 6 distances. The average of those 6 pairwise distances would give us the average linkage measure. Okay?
Yes, 6.
6. He's quick. Okay, and then so these are the first 3 measures. The last one's called centroid linkage, which is not used as commonly.
But you don't have different colors with this pen.
Actually, I do have different colors. Well, okay. Centroid linkage, we take the centroids of each cluster first. That's the average, right? The middle point. There we go.
You can stay, Boo.
Oh, I don't want to. Okay. And now, so these points are meant to be the average of these 3, and this one, the average of these 2. The centroid linkage is how far apart the centroids are, these 2. Okay? So that's the third measure. The ones that are used most commonly are complete and average. Okay? Single linkage, if you have a look at this, in our book there's some examples of it. Single linkage has a problem that tends to produce long stringy clusters, so it tends to join one point at a time as a cluster. Whereas complete and average tend to produce trees which are they're more balanced, more symmetric looking. Centroid linkage is common in genomics. It has some problems, though, with what we call inversions, which we won't discuss, but you can read about in the book. So there's these 4 choices of measure, with complete and average being the most commonly used.
Great. One picture tells it all.
Yes. But if you want details, the previous slide has all this in words. Let's see. Okay. So a few more things to talk about. We talked about the complete average and single linkage and centroid in the previous slide, and that was to do with how far apart we deem a pair of clusters from each other. But then we still have to we have to decide, what do we mean by far apart, right? And we've been using square distance up to now, and that's the Euclidean distance, and that's actually the most commonly used measure. But another one that's used quite commonly is correlation, okay, which is the correlation between the profiles, the features across, 2 observations across their featers.
This is often the case when features are actually measurements at different times. So you can think of each measurement for an individual as a series of points over time. little time series, like each of these curves, and you want to see how similar the patterns are in each of those series. So then correlation measure is suitable in that case.
So yeah, here's an example, and we can imagine this index, as Trevor said, could be time. We have 3 observations, the purple, the gold, and the green. In terms of square distance, if we look just across the coordinates, the purple and the gold are very close together, and the green's farther apart from those two. But in terms of correlation, if we just consider the pairs of points at each of these indices, then actually the green is closer to the gold than it is to the purple, right? Because the green and the gold go down and up together, right? So the point is that correlation doesn't worry about the level, but rather the shape. So if shape is in your example is in particular problem is more important than the actual level, then correlation is a better choice than Euclidean distance. Sometimes, and also you have to decide whether you want to use correlation or absolute correlation. Sometimes it matters whether things are anti-correlated or positively correlated, and other times you just use the absolute value of the correlation. So those are all common. Those are both common.
So I suppose this brings up the point that you can actually come up with any distance that suits you.
Right.
Depending on the problem. If there's a particular distance that makes more sense, you'd use that.
Exactly. The only thing you need for hierarchical clustering, and actually for k-means for that matter, is a choice of distance between pairs of observations. Having decided that, then the algorithms just use that as their input. Okay. So some practical issues. A few more things. Well, scaling of the variables matter, right? And again, that's the case in k-means as well. So this slide actually refers to both k-means clustering and hierarchical clustering, right?
And principal components for that matter.
Exactly, right. If the variables are not in the same units, and one variable is in a unit that has very large numbers, right, then if you don't standardize the variables, that variable will dominate either principal components or clustering, right? Because it's just the units are such that the square distance for that variable is much larger. Right? So typically, if variables are not in the same units, one should standardize them. In other words, make the mean 0 and variance standard deviation to be 1. If they're in the same units, you have a choice, and it's often good to do it both ways. If they're in the same units, you might want to leave the variables as is and see which ones have more variation, and those will tend to drive the principal components or clustering. But in other cases, people will standardize in that situation. So it's good to try it both ways. And then in the case of hierarchical clustering, we talked about these already. Should we use square distance or correlation for dissimilarity? And the linkage, right? Choice of linkage. A problem I've alluded to, I'm not really going to say much more here, is the choice of k, the number of clusters. Right? And let me just say, we're not going to talk about it because it's a difficult problem with no agreed upon solution. There's not a standard method we can point you to say, this is how you choose k. In our data mining book, The Elements of Statistical Learning, in Chapter 13, there's much more detail about this. But typically the problem is, again, it's not well solved, and it's usually done in sort of a qualitative way. Like in a clustering, hierarchical clustering, people just tend to look at the result of the clustering tree, see where the biggest drop in the branches is, and maybe cut it off there. Like we saw, remember the example, and go back just to the clustering. In this example, right, you might, if this was actually some data you had, you might look at this and say, it looks like the longest branches are here. Here's where the longest arms are. I'll cut it off here, and then below that, the arms are much shorter, right? And remember, that's reasonable because the height at which we draw these joins is the square distance at which the joins occur. So the biggest bang for the buck is occurring in these joins, and then there's less lower down. So that's subjective, but that's typically what people do. They just have a look at this and say, I'm going to cut it off, maybe at 3 clusters. Okay. And which features should we use to drive the clustering? Right? You're often given in some areas of science given a large number of features, and you can and you want to use those features for clustering some objects. You can choose the features you use, and if you change the choice of features, as you can imagine, it's going to change the clustering that you get. Okay, that's the end of this segment on hierarchical clustering. In the last segment, we'll see a real example of the application of hierarchical clustering to a study of breast cancer.